Most people think power and energy are exactly the same thing. But in engineering, this is not correct. In this video, we will understand electrical power clearly from the fundamental level and learn why power is one of the most important quantities in electrical and RF systems. Electrical power describes the rate at which electrical energy is transferred, converted, or consumed. While energy tells us how much work can be done, power tells us how fast that work is being done. In electrical systems, power is measured in watts, abbreviated as W. 1 watt means 1 joule of energy is transferred every second. The fundamental relationship for electrical power is P equals V, where P is power, V is voltage, and I is current. This equation tells us that electrical power depends on both the amount of energy available per unit charge voltage and the amount of charge flowing each second, current. For example, a circuit with high voltage but very little current may consume less power than a circuit with lower voltage but much higher current. Power is therefore not energy itself. Instead, it describes the speed at which energy moves through an electrical system. To understand power, consider what happens when current flows through a circuit. First, a voltage source provides electrical potential energy to charges. This energy is carried by moving electrons through the circuit. Passable. Next, as current passes through components such as resistors, LEDs, motors, or processors, energy is transferred from the electrical system into another form. A resistor converts energy into heat. A motor converts energy into mechanical motion. A speaker converts energy into sound. In every case, electrical energy is being transferred at a certain rate. The faster this transfer occurs, the greater the power. Imagine two identical heaters. One converts 100 joules of energy per second, while another converts 1,000 joules per second. Both consume energy, but the second heater operates at 10 times the power level. This is why power is fundamentally a measure of energy transfer speed rather than total energy itself. A useful analogy is filling a swimming pool with water. Imagine two hoses connected to the same pool. Both can eventually fill the pool, but one hose delivers water much faster than the other. The total amount of water delivered is similar to energy. The speed at which water is delivered is similar to power. If one hose delivers 10 liters per minute and another delivers 100 liters per minute, the second hose has a much higher flow rate. In electrical systems, power works in the same way. Two batteries may store the same amount of energy, but one battery may be capable of delivering that energy much faster. As a result, it can power devices requiring higher power levels. This distinction is extremely important because engineers often care not only about how much energy is available, but also how quickly that energy can be supplied to a load. Power is therefore best understood as the rate of energy delivery. Electrical power is a critical design parameter in every engineering system. Engineers use power calculations to size power supplies, select components, manage heat, and estimate system efficiency. For example, every electronic component has a maximum power rating. If too much power is dissipated, excessive heat may be generated, causing damage or reducing reliability. Power calculations also help engineers design cooling systems. High-performance processors, RF amplifiers, and power electronics often require heat sinks, fans, or advanced thermal management techniques. In battery-powered devices, power consumption directly affects operating time. Lower power consumption generally leads to longer battery life. Engineers constantly balance performance, efficiency, and thermal limitations when designing systems. Whether designing a smartphone, industrial controller, satellite transmitter, or communication base station, understanding power is essential for creating reliable and efficient products. In RF engineering, power plays an especially important role because communication systems rely on transmitting energy through electromagnetic waves. An RF transmitter converts electrical power into radio frequency signals and delivers them to an antenna. The antenna then radiates part of this power into free space as electromagnetic waves. Higher transmitted power can increase communication range, but only up to a certain point. Engineers must also consider antenna efficiency, propagation losses, noise levels, and regulatory limits. Power is commonly expressed in units such as watts, milliwatts, dBm, and dBW in RF systems. These units help engineers analyze signal strength throughout a communication link. RF amplifiers are specifically designed to increase signal power while minimizing distortion and maximizing efficiency. Understanding electrical power is therefore a key step toward understanding link budgets, transmitter design, receiver sensitivity, and overall wireless system performance. So today, we learned that electrical power is the rate at which electrical energy is transferred or consumed, not the same thing as energy itself. We went from definition mechanism, intuition, engineering, view, RF application to build a complete understanding of the concept. This foundation prepares us for the next topic, energy versus power, where we will clearly distinguish these two commonly confused quantities. Thanks for watching. See you in the next video.